Hello, everyone. It is a great pleasure to introduce Gökalp. Gökalp is a physics student at Bilkent University in his fourth year. On top of his outstanding success in physics, he's also doing a minor in psychology. And together with Gökalp, we studied hydrodynamics as an effective field theory. I don't know how much I was able to help Gökalp, but I definitely learned a lot from him. And as you will see very soon, he did an excellent job in studying this subject. Gökalp, the stage is yours.
Thanks again for the nice introduction and talking about all of this. So the topic is hydrodynamics as an effective field theory. I will give an outline. We will start by discussing why we use EFT for describing hydrodynamics. We will build this MSR Lagrangian, which will help us complete the building of the effective field theory. This building will be done with Langevin and Fokker-Planck equations. We will then describe how to build these Lagrangians from first principles. Then we will discuss how we detect diffusion using these Lagrangians. And we will produce the Navier-Stokes equations of hydrodynamics, which is the most useful equation of hydrodynamics probably, although it's unsolvable kind of. We will also prove second law of thermodynamics and Bernoulli equation, which has 100 proofs, but EFT is a nice proof also. Okay, so why do we use EFT? The goal is to understand dissipative systems and to describe them in a long length scale, which is synonymous to low energy. Although it was developed for PFT, EFT is able to describe many other systems as well. It has been developed quite a lot. And the nice thing about it is you only need the symmetries of the system to get the equations of motion of the system. So you don't need to know the nitty-gritty details of your system. You don't need to know about the molecules, the atoms, the orbitals. You don't need to know string theory to understand hydrodynamics. This shows. This is why it's a powerful approach, and using it, we will, as I said, prove Navier-Stokes and second law of thermodynamics. So we start by Langevin equation, which is really helpful in describing stochastic, which is useful in describing noisy systems. And we do this by introducing this equation where this psi is just a Gaussian noise, let's say. But the problem with this equation is it is not exact. The formalism of Ito and Sotonovich is different, and it really gives different results when you try to apply it. So we need to have a deterministic solution without the need of subscribing into a prescription. So the solution for this, so the deterministic solution to this we find is the Fokker-Planck equation that's given by this. The A and B factors become like you see in here. And when we generalize to this to n degrees of freedom, this is what we get. And we define partial derivative of t as an operator of w, which will be helpful later. Okay, the usage of this is if you have an overdamped oscillator, which is given by this equation where this is the usual damping and this is noise, then you get this equation with the probability density. P is our probability density. When you Fourier transform this and solve it and then inverse Fourier transform it, you get this equation. And when you take t to infinity, it leads to a steady state, which is the property that many stochastic systems has. That's why we will use it to derive a general Fokker-Planck equation, which will be even more helpful for us. So we also know that probability have to be conserved. So when you get the integral of this probability density over whole space, it should give you 1, and it should stay 1 throughout time. So we need to ensure this condition holds while ensuring it has a stationary state, which leads us to this general operator where Q is arbitrary. This mu is the partial derivative of phi, which is actually Hamiltonian over beta that comes from the partition function. Okay. So we get to time reversal symmetry. This is important because dissipative systems tend to be reversible. So this means you lose energy, and when you lose energy, the system becomes a kind of irreversible. So when we introduce stochastic noise into the system, this allows these systems to have a time reversal symmetry once again. Even though dissipation kind of took it away, we get it back by introducing noise. So that's why it plays such a huge role in building of the dissipative effective field theories. And normally, the constructed W operator messes up the steady state when you transpose it. But if we apply a similarity transformation, which I won't get into, but it's nice, you get a W reversed, which preserves the steady state. So the knowledge of a steady state existing does not imply an error of time, which is important because you tend to assume it that way. But what gives us the information about the time arrow is the initial conditions. So this means W reversed, the reverse W operator also leads us to a steady state. And when this condition holds, this implies Q has to be symmetric, and this will be important later on as well. Now, we have to abandon Fokker-Planck equations too, because they only give you the probability density. We need to have much more, and we can have much more. So we move on to Lagrangians. I hope many of you know it already, but let's go over it quite fast. It's defined to be kinetic energy minus potential energy, and when you integrate it over time, it gives you the action, which is supposed to be dimensionless. And when you vary this action with one of the parameters of your system, you get the Euler-Lagrange equations, which is going to be used for getting the Navier-Stokes later on. These equations of motions can give you the Newton's second law and many other things. Also, the power of Lagrangians can also be used for describing dissipative systems. But Hamiltonians cannot do this because they conserve energy, and this disrupts. This goes against dissipative systems. Now, MSR Lagrangian is built by Martin, Siggy, and Rose in 1973. They want to have the probability of going from Y to Z with this operator, but they wanted to do this from path integrals and from the EFT formalisms. So they introduced this. This is a regular path integral developed by Feynman. And when we start with ITO, we put the Langevin equation here, and we get the noise average. So integrate out the size. And then when we get the integral, we get the probability of going from Y to Z with delta t. Where this delta functional is an interesting term. It's defined to be, it's a generalization of the delta function, we take the dimension higher, and then we make the sum continuous, and then we get the delta functional, which is used here. And when we then apply the psi integration out, we get that our MSR Lagrangian is the following. But we have this AI here, and we don't like it, so in order to get rid of it, we will use Fokker-Planck once again. So although it's possible to go from Fokker-Planck to Lagrangian, it is messier, so we only go from this to this equation here. We identify what AI is from the Qij by applying this transformation. But the problem is it's not exact because this del J Qij has to be 0 for this to work. But it's not always 0, and it's apparently creates problems for regularization. This we will not get into right now. But in the end, this is the equation we get from using Fokker-Planck, getting rid of this A term. an example of this is the dissipationist. We can go from the dissipationist Klein-Gordon theory, which is used a lot in QFT formalism. We can get the MSR Lagrangian first by using some Poisson brackets, and then we can add dissipation and noise at the same time. That's what we introduced. This was the term we had before, as you can see here. We only take Qij to be constants, and then using this Hamiltonians, we can get the mu's. And then when we solve these systems, we get that it relaxes towards an equilibrium because of this term right here. That's what quasi-normal modes mean. It has a complex factor. Now, how do we build these LSMRs in general for any systems? We start with the part we know. Else will be always equal to di x dot I minus Hamiltonians, but this is not the same as the phi over beta from before. This is another object like these Lagrangians and like LSMRs are not equal. H and HMSR is not equal also. Now, in order to have the noise in the system, we need to ensure that when pi goes to 0, the Hamiltonian goes to 0, and imaginary part of it is below 0, below or equal to 0. This ensures the noise variance is non-negative. Now, and we need to ensure time reversal symmetry. This comes from Fokker-Planck equations also, the proof I showed 2 slides ago. H must be invariant under time reversal transformations, which take pi to pi minus I mu. It's minus or plus, which ensures this xi factors to go away. And we need to have strong symmetries. I will give an example of this, but consider one f that doesn't change through time. H must be then invariant when we take pi I to pi I plus del IF. Now, what is this strong symmetry? And an example of this is angular momentum conservation. We know that this SI does not change, Einstein's summation convention. So when we take the derivative of this with respect to time, it's 0. Then we can say the Lagrangian that we are going to write has to be invariant under pi I going to pi I plus 2 SI, because partial derivative with respect to SI of this is just 2 SI. Like x squared to derivative of x with respect to x. Okay, now what do we get when we only have one conserved quantity? We define Q to be charge or mass, which has a density defined to be rho. And conservation of Q immediately implies taking the derivative of this, that pi plus lambda. In order to build an invariant building block from this, we need to have that lambda disappearing. So we take the partial derivative of x, partial derivative of x. Now, combining this with time reversal symmetry, we get this term that has the same form we had from before with Qij's. Now, when we solve this equation using this mu as coming from a thermodynamic potential from a Gaussian density, like remember that this was Hamiltonian's derivative with respect to a coordinate. When we take this Hamiltonian to be a Gaussian density, then we get the diffusion equation, which comes out automatically just by introducing time reversal symmetry, noise, and one conserved quantity. Now, without time reversal, you can have other terms. You can just have partial derivative of x of pi without using another factor. Remember here, we have 2 partial x's because we need to cancel the we need to have the time reversal symmetry. This is odd in time reversal symmetry, but when we introduce another, it conserves T symmetry. And when we do this, we get another equation of motion from the same time order thermodynamic potential, and it turns out to be a biased diffusion. Without time reversal, we had this one. With biased diffusion, we have it moving. So now we can tell the arrow of time just by looking at how the system evolved. But from this, we can't really tell it. Now, how do we detect diffusion? We use PET integrals, but we use 2-point correlators in order to understand how the density change in one point affects the density at another point in space-time. Now, in order to compute this, we use the Lagrangian that we had from before, and then we take this integral with some neat tricks. I can explain it to you if you ask some questions about it, but we don't have time much here. And the result turns out to be this one, and the poles of this correspond to the quasi-normal modes. So remember we were measuring how the density change affects another point. This gives you the poles gives you where this is largest. This correlation is largest. So that's why the poles correspond to the quasi-normal modes. Now, can we just add other terms? So we only had one term, but there are many terms you can write that conserves T symmetry while respecting strong symmetry. We can, but they turn out to be zero when we go to long length scales. So if we define x going to x over lambda, a conformal transformation in a way, this means the scaling the dimension of x is -1. And we can't find the dimensions of the other variables. So t turns out to be -2, rho, pi, and mu equal to d over 2. D is the dimension here, as usual. So when we write an arbitrary term like this, we realize using these quantities over here, it's always greater than 0, which means when we take lambda to 0, these terms are going to disappear. So low energy ensures that the only term we need to be concerned about is this one right here. How about when we break T symmetry? It changes things. Then you find that the scaling dimension of T is different. And this shows in how the system evolves. Standard deviation changes because your invariant now has changed from x squared over t to x to the 3 over 2 over t. So for Navier-Stokes, let's go to like our aim from all the way back. We need to show Navier-Stokes equations using this Hamiltonians and action of SMR. We know that in these systems, physically, that mass, momentum, and energy has to be conserved. And these are the densities of these objects that we will use as our variables in the Lagrangian. And if we take Hamiltonian to be these, where these are just the currents of the conserved quantities, where Ji is the mass charge current, epsilon is the energy current, and tau ij is the stress tensor. This ensures automatically that continuity equation holds, which is given in 22. And using rotation invariance of the currents, which is supposed to be the case, first law of thermodynamics, and Gibbs-Stone relation, we get that the currents are given by this equation. And adding noise and dissipation, like we did from before, while introducing this viscosity tensor, we get the continuity equations that I described from before. But adding noise, we automatically get the Navier-Stokes equation, And from the 25th, we get the most used Navier-Stokes equation, which is this one, where the term inside these brackets is defined to be the convective derivative. So entropy is defined to be this in thermodynamics. When we write it by this notation, we get that from the equations of motions of the system. This is just the abstract form from before. We get this equation, and notice that it looks like entropy from before, this part. It's specifically this part, just by taking the derivative and multiplying by mu I, we get this equation, and then we notice that this is a total divergence term, so it should go to 0. This one is entropy current automatically, and since this is non-negative, as we said from before, we ensure the entropy is always increasing. Now, Bernoulli equation is proved from the 25th equation, again, that I gave right here. We go from 25th to 26th, and then we assume this rho doesn't change, and we have incompressible flow, which ensures the divergence of B is 0. Then we automatically get the Bernoulli equation, just by applying some things. And effective field theory, let's wrap it up. Effective field theory just required the knowledge of the strong symmetries and time reversal symmetry. So we didn't do tedious work from building from quantum mechanics. We only used some terms, added some terms to the Lagrangian, and solved for the equations of motion, and then we got Navier-Stokes second law of thermodynamics and Bernoulli equation. More importantly, we didn't just describe hydrodynamics, we described all of the dissipative noisy systems. And this formalism can be used for many other things. And hopefully you got something out of it. And if you have questions, I'm ready to take them. Again, thanks Ege for all his contributions. And I hope this program continues forever because it's very nice.